So, J-pole antennas, or how I learned to stop worrying and love Ed Fong. Full of them. A J-pole is, real briefly, an end-fed half-wave antenna fed by a folded half-wave dipole, sometimes called a quarter-wave stub. That's all you need to know. Good night. Let's start real quickly. Real basics here. Why a J-pole? What is it? Well, it's an antenna, obviously. An antenna, it's a piece of metal that can turn some alternating current into radio energy. It can also do the opposite. It can take some radio energy and turn it into alternating current that your radio amplifies, and you get to hear things. It's usually made of wire, it can be made out of tubing. We'll talk about that later. Frequently, and not always, but a lot of the antennas that we use have a quarter wavelength that's connected to one part of your coax, the inside, and a mirror image quarter wave that's connected to the shield of your coax. Quarter wave plus quarter wave equals a half wave. That's a dipole. Di for two, we've got half of it, a quarter on each side, so we call it a half-wave dipole. One way or another, most antennas can be looked at from the right angle, and what you'll see is a half-wave dipole. Sometimes it may not look like it. We may have a vertical. The other half of that dipole might be the shield on your coax. It could be some ground planes or counterpoises that are stuck into the bottom of it. But most antennas, not all of them, but most of them, 2 quarter waves makes a half wave. When we do that, oh, I got a pointer. Yeah, look at that. Whoa. I can't get over myself here. This is so this would be our coax where we feed. Most of you, if you took a general course and you tried to make a 20 or 40 meter dipole, this is what you did. You had a quarter wavelength here, quarter wavelength there, coax here. We get our alternating current wiggling back and forth with nice pretty sine waves on that antenna. And as it happens to be with this half wave here, towards the middle of it, we get very low voltage, but lots of current. The current and the voltage are always 90 degrees out of phase. If you've done a general class, you remember this, or you may not remember this. If you haven't done a general class, starting September, Saturday mornings, we can talk about this. If you're not familiar with this, take my word for it. At the very center of that half-wave dipole, the current's very high, the voltage is very low. Since a lot of current can flow, it's not being impeded. That's another way to say the impedance is low. The way we feed this is using our coax, and one of the features of our coax is that it can carry a lot of current at very low voltage and pretty low impedance. That's just a feature of coax. So I'm going to leave that there as a reminder. Most of them are dipoles, we've said that. That's what we have at the feed point. Low voltage, high current. High current means low impedance at the feed point. Low current at the ends, though. Look what we have at the end. Where'd my pointer go? At the end of the dipole, we have very little current, but we got lots of voltage, right? Do you remember hearing how you should put your dipole high enough so that nobody can touch the tip of it when you're transmitting? The more voltage you have, the more likely it is to jump a gap and give you a little snake bite. That's one way to remember where the voltage is high. It's at the ends. We're gonna come back to this because it matters for J-poles. This is why we use low impedance feed line. That matches the center of a dipole. And there we have it. Most of our half-wave dipoles are center fed, but not all of them. Here's some examples of half-wave dipoles. In the middle we have what you see a lot of the time. They're not so common anymore. Most people use vertical. At some repeater sites or commercial things, you might see a folded dipole, but still essentially a half-wave dipole. Of course, most of our HF dipoles, that's exactly what we're dealing with. Oops, that was backwards. Sometimes that's not the best thing that we want. Sometimes we need a vertical top of our car. It'd be a lot harder for us to put one of those center fed dipoles on top of our car, isn't it? So we use a quarter wave mag mount. Your car is the other quarter wave. It's not very efficient, but it works. It's really portable. So we live with it. Sometimes the middle of the antenna is a hard thing to reach, especially when you get into HF antennas. A lot of people doing POTA and SOTA like to bring end-fed antennas just because it's so much easier to get it in the air. A half-wave dipole will give you, a lot of the times, a much better gain pattern than you'll get from a quarter wave mag mount on your car, for instance. Here we're going to have a little hard to read because of the colors here. The green line right here, whoopsie daisy, what just happened there? Was that me? No, it wasn't me. Here we have, the yellow line represents what you're going to get from a mag mount or another vertical. Really good one out here, much better gain than down at the horizon is a 5/8 width vertical, but a half wave center fed dipole is better than that quarter wave with a ground plane. So that's one reason we might want to do that, a little better performance. When we're sending energy up into the air like this, that brown one with the extra high lobe that goes way up here, that's not very helpful to us, is it? And I want you to remember the shape of that because we're going to talk about 440 in a while, or 70 centimeters, using your 2-meter antenna for it. So going back here, we've got our half-wave dipole now. What if we wanted to feed it some other way from the end? We would need something here that could provide very low current, but very high voltage and very high impedance. Coax isn't going to do that. Can anybody think of something that has, oh, I don't know, high voltage and low current that we could feed this with?
Ladder line.
Okay, ladder line. What did I hear over there? The end of a dipole. Of course, the end of a dipole has exactly the features we're looking for, doesn't it? Right? So, what if we stuck the end of a dipole on there? Piece of cake, right? Now we can feed that from the end. Can you just hold that up? Pretend that's your half-wave dipole. Now we just need to make another one. Stick that on them there to feed it. And I still have to feed that in the middle, and really that hasn't gained me anything because I still have all this to deal with, and it's kind of a bother from there. I'm going to take my other dipole here and fold it in half. Now my feed point's here, and I'm driving that antenna. Now what's interesting about this, I'll grab it back. I still want to think of just a stick. You're not looking at a J-pole yet, just a stick. That's still being fed, it's being fed at the end, but the center is still that point right there. This is a solid connection, and here we're drawing one without a solid connection, but you know, AC is funny. You can do that and get away with it. I'm gonna leave that to that. So we can feed a dipole and fold it up like this. You're going to mess up all kinds of things because the two legs are now going to capacitively interact with each other, and there's ways to compensate for that to get good SWR. And the way to do that is you just start creeping your feed point up. Sooner or later you hit a spot close enough to 50 ohms that you don't care about it anymore. And I'm sure you've all noticed on J-poles, it's fed up a couple of inches, right? Now you know why. Right here, ignore everything on this side of my hand. We're looking at a dipole. It's folded over there, and the feed point is squished up to compensate. That is being used to drive this dipole. The center of it's right there in front of my face. See, we've got our 2 quarter waves there, quarter wave there, quarter wave there. That's all that's going on. I keep bumping this, jumping the gun. the lengths you find in this, we have calculators that give us dimensions to make these down to hundredths of an inch, and it looks very complicated. But from here to here, whatever frequency you want to pick, whatever wavelength, that's half a wavelength. It's about a meter for a 2-meter dipole. That's about a quarter wavelength. 2 quarter wavelengths. So there's our folded dipole feeding a half wave. By half wave, let me do it with a pointer. You can still see that the orange shows half the sine wave there. That is the voltage. The blue shows the current, very high in the middle, very low at the end. And this dipole here, you see both of it. The current's low in the end, the voltage is very high at the end, perfect for feeding. So we've taken 2 antennas and stuck them together end to end, and then we get 1 antenna. This is an old idea, and you see here the patent goes back to 1909. You could probably recognize what's hanging beneath the balloon there now. It's a lot like that, doesn't it? And look at this Zeppelin. I bet everybody recognizes that now. So, congratulations, you now know what a Zeppelin antenna is and how they work. Obviously, in a balloon or an antenna, it's really hard to access the middle of the antenna. It's really easy to access one end. It's that simple. That's all we got about J-poles. There are some modern ones that you can get. Alpha antenna makes several, actually, ZEP antennas, or J-poles, whichever you want to call them, for HF use. You can see how the 2 legs hook up onto the base unit there. You can make one with a piece of ladder line and a single wire off at the end. You can also do weird things by adding another half wave off of the other leg. Another half wave can be added off of this end of the stub, but it doesn't gain you a lot in our purposes. The G5RD is a good example. A lot of ways they can be put together. We tend to use number A most of the time in copper pipe J-poles. It's very easy to make. They have as we saw in that thing with the radiation patterns, it's a flatter pattern than most verticals are, which means out on the side, actually looking to talk to people, it's a lot stronger. With the C there, the top of it folds down and comes back on itself. We usually will call those slim gems. They're very much the same. That extra half of it coming down the other side doesn't have a huge impact on the performance or the length of it or anything. It's there, but it's not huge. And there's a lot of antennas like this, sometimes made with ladder line. Houston made this one completely from scratch. It's pretty cool. Pass them on.
It's not for sale.
And what's the price?
Plato said every man has his price. Plato did not say that. I made that up right now. I could get into talking about the details on the radiation patterns and the gain that you can get from J-poles. You'll find if you start looking at this on the internet, people love to argue about it. I mean, love to argue about it. I mean, they get really committed to arguing about it. I don't care a lot myself. There are differences. Yes, there are absolutely differences. Can I hook a radio up to them and notice that difference? Absolutely not. I think this is noticeably better than a mag mount in your car. If you're going to use a mag mount at home on a pizza plate, this is going to beat it. But if you want to talk about buying a nice diamond antenna for 2 meters and compare it to this, yeah, there are differences, but those differences are so tiny, you're going to have trouble measuring them. So I'm not getting into it. Not likely noticeable. Instead, choose your antenna based on what it's going to cost you, the availability of it, and what you want it to perform like. That would be things like, do you want a portable antenna? This one's really portable. J-poles are portable, but they're kind of a pain. They're kind of big. A lot of people will put a joint in the middle here, a screw joint, so you can knock them down and put it into your trunk. I usually build that into mine. But it's not something I could walk around with my handheld. Not frequently anyway. I can do it, but it gets old. 3 common ways to do it: plain old wire, ladder line, and copper pipes to make J-poles. The ladder line in the middle, it's cheap, it's flexible. You can make Slim Jims with them. You can make headphone style antennas that we'll talk about in a moment. You know, it's great. Over on the left is a wire one. You can hang those up. I think Houston, who made this one, this is made that he puts it on a telescoping pole, hooks it to the tip, and then just shoves the pole up. And it is good for being portable. And lastly, the copper pipe. If you want to do a installed antenna that's going to be up all the time, it's very good. There's another big difference though. Houston, tell us when you made this and what happened when you tested it.
Well, I made that for 144/100 for 2 meter CW. But I thought that I'd be able to scroll around a little bit with a VFO and operate on 146/580, etc. But I found out very quickly that the SWR went up fairly dramatic as soon as I got out of the 144 megahertz area. So I talked to Keith, and I knew he was going to school me up on it. And I think he laughed at first, and he started talking to me about Q.
Let me interrupt. I laughed quietly and privately to myself. Go
But
ahead.
I'll tell you, the antenna really worked well. It was 1-to-1 right in the area where I wanted to use it. And got some really good contacts, some long distance contact. I used it today on Cable Mountain, and it operated just perfect, super lightweight, works great. It's very rudimentary. I think it took me 10 minutes to solder up. But I tend to use it a lot. I like it. It's easy, lightweight, weighs nothing. So anyway, you're welcome to take a look at it, and I'm sure there's other ways to perfect it, but it works pretty good. But Q was an interesting concept, and it kind of took me back to probably one of the exams that I took at some point. So
Yeah, we cover Q in the technician and general and extra class. Most of the time we think of a high Q antenna. It's tricky to tune, and it tunes in a very narrow range of frequencies. Low Q means you'll tune over a wide range of frequencies. Most of us think we want a really high, low Q antenna that tunes a wide range. Sometimes you don't. Around town here, it can be a very noisy environment. If you're making a 2 meter antenna for a packet station, why not have it made for that one frequency all the time with a very tight Q that won't be bothered by other stuff going on around it?
Keith, you said, what is the material that separates the 2 wires?
Houston, what did you use here?
that, I had a really, probably 1950s, whatever, spool of 450 ohm ladder line. And I just used a chunk of it, and that's it. I think you can use any 450 or maybe 300 ohm ladder line for that matter, but very inexpensive.
Yeah, the 300 ohm window line is most common. This is cool because it's just kind of antique looking. Jeff?
In trying to tune a copper J-pole for, let's say, the middle of the 2 meter band, how do you fine tune where you're going to be looking for that center frequency? Is it moving the connector from the coax hot center feed line up and down the J-pole, or what?
Both sides.
Both?
You want it to be parallel.
Okay.
It's not a terribly picky thing. I have seen people with them mounted one higher than the other,
Right.
and you know what, the antenna works. Obviously, at some level, there is going to be some loss in performance. And also, just as obviously, we're looking at, if we're making it for VHF, it's a line of sight mode. And even at 5 watts, we're blowing power out that we don't really need. We got a lot of room for a lack of efficiency. Another quick diversion there, a lot of people make them so that the ground is hooked way over here on the side, and the center conductor is hooked over on the other side. That's not technically the correct thing to do either. Both sides should be the same length. Let's see if I can back, oh, you can see right here, the little circles hoops they've jumped through to get the both sides of the coax the same length to the viewpoint. It's important to do, you want to do it the right way, but if you don't, it's not really going to matter a lot. This is still a great antenna, even though it's not built with the equal length leads.
And Keith, the radiation pattern, is it like, does it throw like a donut on the horizon, or is it more at a 45-degree angle?
It's a donut in the horizon, just like that, we can back up later. It's lower to the ground than you get from a quarter wave vertical. It's going to be pulled down a little lower on the side of the stub. So if you're really marginal on a signal, there's a repeater you use most of the time. When you put this in your chimney, you put the stub in the direction of the repeater you're most likely to reach. But that difference between this side and this side, it's minuscule. It's there, but I bet if you went around with a field strength meter, you'd be unable to detect it. I know, I've tried. Field strength meter turned out to be, the only value it ever gave me was showing me just how much I need to stop really lying about certain things. And it was a good investment for that. The copper pipe, everybody should remember that the radial energy always travels on the surface of the conductor. This has an awful lot more surface area than this. And what that means is that this will be much more broadbanded. And one of the advantages of our copper pipes, the last build session we did 2 years ago, everybody's antenna left at being about 1.3 to 1 or better over the entire 2-meter band. Over what, 4 megahertz? That's a big spread and an excellent SWR the whole way. As he was saying, this was 1 to 1 way down at the bottom of the band, and as soon as he tuned off of that, it went through the roof. How bad did it get by the top of the band?
Well over 3. Well over 3. You'll tell about the calculator? Or doesn't matter?
Oh yeah, and there is a calculator for coming up with the lengths and all sorts of that. I'm not going to go too much into that, but we will at the build session on the 30th, where everybody's going to go through the whole process of figuring out just how long to cut the copper, and if you want it to be a packet antenna, we'll cut it to be optimized for packet. But for the most part, we're going to cut all of them to work on the entire 2-meter hand. Here we have the catch about these. Because so far it sounds like a pretty killer antenna, and why wouldn't you make it for everything? Well, we all know that most antennas will also work pretty good at 3 times the frequency. And our 2-meter antennas almost always work acceptably in the 70 centimeter band, 440 band. Oh, I'm going to need to use the board over here. We have our vertical half wave here. So it's going to look like that. At 3 times this frequency, it's going to look like this. It's still going to resonate at that frequency. It's going to work okay. It's a little sloppy if there's any imperfection at the lower frequency. It's going to be tripled at the higher, actually probably cubed at the higher frequency. The higher the frequency gets, the more you notice the imperfections in the antenna. But something much more important than that happens. That becomes a 1.5 wavelength antenna in the 440 band. Because this portion of it is 1.5 times 70 centimeters. I wish I had a better diagram to give you. I considered drawing one myself, so I drew one myself and decided, no, autofocus is better. Here is the quarter wavelength antenna, a side view of what its strength looks like. We get down here to the half wavelength, and we can see it's a flatter pattern. It's stronger down at ground level. We're blowing off a little less energy up higher like we are there with quarter wavelength. But when we get to the 3/4 wavelength or the 1.5 wavelengths, we start getting a pattern that looks more like this. So when we're using one of these J-poles for 440, you see how much of that energy is going off of about a 45-degree angle up into the air. Ed Fong says you lose about 8 dB worth. He's got a really good antenna that he's selling, so maybe it's less than 8 dB, I don't know, but it's a lot. For our purposes in this county, we're rarely so far away from a 440 repeater that this still isn't good enough. So that's why these are fine. But something can be done about it. Over here on the right side, we have what would be the solid copper pipe on here. An Ed Fong antenna cuts at the wire and puts a stub over here called a decoupling stub. Essentially, at about a third of the way up this antenna, it makes everything above it invisible to 440 megahertz, but it's still visible at 140 megahertz. He's cut it down to a shorter antenna, and all of a sudden now you get the flatter pole again. So if that's going to be important, if you need an antenna that will do 2 meters in 440 and have a very low pattern for both, you need an Ed Fong antenna. We're not building one of those next week, but they really do, he sells them. Remarkably good price for what they are. Well under $100, and they're beautifully made by his own grad students. So it is an option that exists. Doesn't feed into the copper pipe J-pole. I have not seen anybody build an Ed Fong out of copper. Has anybody here? Maybe not, okay. Why would we do it out of copper pipe then? We've just shown that it's really bad in one feature for 440. Well, if you're going to install it somewhere, you can't beat this for the price. It'll last for years outdoors. It's strong, very low tune Q. It's going to tune everything. Love that. Like we say, very low SWR, the entire band. At our last build session, we had a QST magazine and we're pulling out antenna commercials from Comet and Diamond and things, and their claimed SWR figures were all significantly higher than we were actually measuring. And I'm sure their claimed numbers were as favorable as they dared to make them. Build sessions are a lot of fun, they always are. Even though copper's expensive, it's still a half to a third of buying a commercially made antenna. Long lasting, we covered that. And here's something important. Compared to that RIP antenna that came on your Baofeng, you could be looking at a 10 dB gain using one of these. That's like all of a sudden pumping your 5-watt radio to, gee, how much is 10 dBs do?
10 times.
10 times. That 5-watt radio would act like what?
I would say 50 watts. It'd be nice if you get 100 dB, but you know, I'd actually take 20 dB. That would be cool.
That rubber duck will probably catch on fire. If he wants it, but what happens is that your Baofeng's going to be a much easier radio to hear. One of these. That's
I use the J-pole in Camarillo and talk to the repeater 60 miles away on Sandy Head speed, using a Baofeng 5-watt.
Yeah, we can go a long way with line of sight. We don't tend to think of it in Ventura County because we don't get long lines of sight. But Baofengs are great for ISS repeaters. That's 400 miles each way. So this is the build session. Next September 30th, 8 a.m., right in this very room. It's gonna cost about $40, but Chuck, we expect it to come in less, is that correct? We have a sign-up sheet back here. You can tell me, you can tell Chuck you wanna join, but if you put your name on there, you know we've got your name. We will be buying the materials next Thursday or Friday, right before the class, and that's when we'll be able to get a bit of a refund.
Are you sure on that date, 30th, is a Tuesday?
August, sorry.
August, yeah.
Oh, no.
Where this says September is a mistake. That's part of the comedy.
It's okay, I made one of these.
Look, if that's the only mistake in this presentation, you're all very lucky. August 30th, it's a week from Saturday. Build sessions are always a lot of fun. You will get to do all of this yourself. We will be with you to make sure nobody cuts their pipe in the wrong place. I'm gonna solder it. There's only one of us that's gonna do the torch. I have two, but yeah, I woke up one night in a cold sweat thinking in the news headline, a ham radio group burns down 1,000 Oaks Sharp City. And I thought, oh my God, I'm gonna get a call from
Fun
Stu
was
about
had
this.
by all.
I'm gonna get a call from Stu.
Can I bring them up?
That's about it.
And marshmallows.
I want to thank Dick Reed, Dave Kessler, KK40BI, Wikipedia that I took a couple of drawings from. That's the end.
Dan had a question.
Yes.
Me and I were 180 degrees out of phase.
90 degrees, aren't they? 90 degrees out of phase.
Anybody else have questions?
Copper tends to corrode. Do you put some sort of clear plastic spray on it or something?
I never have. My oldest one's about 15 years old and it's still fine. I certainly wouldn't suggest that you don't do that. But copper builds up a nice patina. Oh, he was asking if it's because copper corrodes, if you need to put a clear finish on it.
What about guys went under the air for 30 years? That still looks great.
You don't want to clean it off every year because then you're just going to restart the corrosion. Houston.
Just like
Yeah, should it be grounded in any way? It seems to be just free air antenna, works great just like that, but if you were to ground it, how might
Anytime I hear a
that?
ham say the word ground, I know we're in trouble. Whatever's going on below this bit right here, it's invisible to this antenna, it doesn't matter.
It's maybe for lighting.
Yeah,
Yes.
yes, for lightning, your mast and your antennas should be grounded, but it's not part of the antenna's performance.
It's
Also, with this part down here, this is just for mounting. You can mount that on a metal pole, whatever you want, as long as that pole doesn't extend up all the way to the bottom of that crook. Martin?
because of that, I think you find you'll need a couple of turns in the coax.
Okay, that's another one of those things we need to talk about. You will hear everybody say that the coax connected to this needs to have a choke at the feed point.
No, it's not a choke.
And they will then tell you to wrap the coax around 5 or 6 times. And the way everybody says to do it, sorry. Everybody I know is in this room is calling. Yeah. You'll hear everybody say that you need to do that, and everybody does that. Well, first off, if you just roll that thing around your hand with the coils going any old which way, it's not doing a damn thing. It works just fine. You can connect the antenna just to the coax right to it, it works just fine. If you want it to be a choke, it needs to actually have the coils nicely spaced and tight together and in order and not crossing over each other. If you have enough coax to do it, sure. I've never heard anybody say that there's a disadvantage to it. I've never seen a demonstrable advantage. Again, this is a dipole. Once you fed it, it's nice to have a choke at the feed point, but it's not a vital thing. It's just like your 40-meter dipoles. I think it's, if you're just going to throw chokes at the coax, do one at the radio end because you're more likely to reduce your noise that way too.
The only comment I was gonna make in addition to that is there is what's called the ugly balance, which is a design factor of taking about 8 or 10 spools in your coax and just globbing them together. But it primarily is used for HF because you have a lot more difficulty with common mode with HF. And really, that's what you're trying to fight is the common mode coming back into the shack. Doesn't have much to do with your actual SDR or SWR.
And if we think about noise in HF, it's really vital. It's part of every every moment of playing in HF is about signal to noise ratio. When we're using FM, like we usually are with VHF, not really. We're dealing with a modulated encoded signal to noise floor. If we get our signal, it decodes it for us. We don't tend to hear the hiss in the background so much. So you're not likely to notice the benefit of common mode shows. Common mode's another fun one to start complaining about because it's only in the shield and therefore it's not common.
I call it uncommon mode choke personally, but
Any other questions? Oh, let's take a break.
yeah.